Okay, so we're back again. Sorry for this problem that we have, and
So as I mentioned earlier, so with binary compounds, the choice of hybridization becomes ambiguous, and we also need atom-resolved density of states actually. The other thing I actually mentioned was that, which as this figure illustrates, that when you have binary, ternary, or any alloy, you potentially have more than one and many possible terminations, and which have different distribution of atoms. Uh, and then each separate termination will have a different binding energy, and as a whole, a statistical average should take care of some sort of, or should be some sort of average of these configurations or stages. So we proposed a sort of an averaging scheme, in which case at the moment we didn't actually care much about the surface distribution, but the electronic inequivalency. So here it goes. So basically, if there are n number of inequivalent positions for the impurity, each with binding energy, let's say EI, we propose a weighted average W as this binding energy. So sum over I, WI, EI, where these are the weights defined through the sort of density of each side. And how do we do that? So we illustrated this in this following way. So suppose we have a binary compound A2B4, in which we'll have an overall density of states of atom resolved A, B, but we also have each atom resolved density of state of each inequivalent atoms, uh, which notionally, so there are 6 atoms in the unit cell, which we label A1, A2, B1, B2, B3, B4. From the electronic data that we actually get from a flow, if we find out that A1 is equivalent to A2, B1, B2, B3 are equivalent, but not with B4. So based on purely the weight, the relevant DOS of A1, B1, and B4 should have weight 1 over 3, half, and 1/6. And that's how we actually calculate the average binding energy. This scheme we actually can easily extend for binary, ternary, etc. And with this, we actually attempt to provide an overview of the reactivity of these alloys. So here is a workflow of sorts where, I mean, we get the data from the A-flow, process density of state, inequivalent atoms, anything else that we want, and then that information goes to the NA descriptor, and this data is plugged into the NA descriptor, or basically a model for binding energy, and that gives us a binding energy EB for ABXY, as you recall. So that's a typical formula for AX and BY binary. Similarly, for ternary, it would be ET of a function of A, B, C elements and their fractions X, Y, Z. Now, before we actually go to show the trends, I just like to show the abundance of these compounds. So what we, when we actually searched for the D block binaries on the A-flow database, uh, so this color graph basically shows the abundance. So it's not that all possible binary combinations actually do exist, but they what we have to work with is these metals based on availability. If we extend uh, and we don't force them to have an ICSD number, which means that these are potential compound. They may also exist, may not. So that then somehow, I mean, then also we don't get much increase in the database. Now here is the actual result. So here what we actually show is the binding energy of these compounds. So as we mentioned, the binding energy is a function of A and B, as well as their sort of fraction X and Y. So what I actually map is, and that's basically 4-dimensional database. So we simplify this to have a 2-dimensional chemical space for A and B, which is 3D, 4D, 5D, and similarly 3D on the y-axis, 4D y-axis, 5D compound. And we calculate the minimum and the maxima of the binding energies for all the XY candidate that we actually found. So and so the upper, the lower semicircle, and okay, so this data each has this circle which is two semicircle. Each of those semicircle has a color which is proportional to their binding energy, and the lower semicircle is the minima of the binding energy, upper semicircle is the maxima of the binding energy. So this gives us a trend. So more reddish sort of pairs of semicircles or circular blobs are relatively better candidates, and things that are in greenish or bluish, they are extremely bad candidates for corrosion. However, this was reactivity against oxygen. It slightly shifts and changes also in scale and some trends when you compare this with silver. However, the red spot, so to speak, if we go back, so this area, this area, this area, they more or less stay the same. Uh, there's not a systematic shift or so. And what we learn here is that the stable alloys against potentially corrosion are generally off diagonals in each of the subblocks. We also actually plotted sort of the energy of the least and the max reactive sites. If you recall, I mean, we had, let's say, A and B, which have several inequivalent sites. If we pretend that each of the site, I mean, the adsorbent binds to just that site and use that atom resolved density of state, so we get an estimate of the sort of binding energy for that particular site. And this I'm not sure actually, I mean, for a video conference, I mean, whether can one can read or not. This actually tells us that in certain cases where there is a large contrast of the site reactivity, but from this they seem, from the overall average binding energy, they seem a good candidate. One has to actually be a bit careful this estimates may not actually work. Or I mean, our predictions has to be taken a bit of a care, and for that we actually did this calculation. This is the same trend for sulfur. Here the contrast is somewhat less staunching compared to oxygen, but it is nevertheless there. Uh, Among ternary, actually, we found relatively much less number of compounds. So here is actually list where we actually can color code uh, the ternaries in terms of binding energy. So the stable candidates are basically red, from the red side towards the orange side. This is for oxygen. This is for sulfur. And here is a bit of a summary. So what we found is that the number of D block alloys overall after removing duplicates, etc., were basically 800. Ternary were 50, and quaternary, we didn't find any actually quaternary metals somehow. So and these were the 50 compound that we actually showed the color code. And what we learned is that typically the stable alloys among binaries are the off diagonal, which means that a D0 to 3 sort of electron occupation metal, if combines with D7 to 10, they find a bit more stable binary. Uh, and with this, it concludes the processing of the D block alloys. The next thing we actually thought was actually to reduce chemical space based on human intuition and from something that we learned from this analysis. So if we consider only elements that are in main group or late transition elements, we will have much smaller number. On top of it, if we use the human knowledge to remove things that are actually toxic, hazardous, or very expensive, we can further filter this, and we get a following tentative representative list of 12 compounds. One can argue this could be 10 or 15, but this is a representative reasonable set. This gives us about 66 binary choice. From these binary choices, IFLO has 136 binary, which is one fourth of what we were looking at in D block systems, and just 15 ternary compounds from this set. And this is the list of those compounds. Now, we some of these compounds which were from the D block, we already have the data to guess whether they are good or bad candidates against corrosions. But inclusion of aluminum, silicon, etc. Uh, uh, creates a bit of problem because our model crucially depended on the hybridization which we took from the earlier literature, and at the moment we didn't have that data for every atom or compound. So we looked for another alternative, and one possibility emerged. That was, I mean, we already have tools to access data, so why not try to choose a data mining plus a chemical reaction approach. Now let's see what this is, and this is not going into details of chemical reactions and looking at kinetics, etc. We're just trying to look at the very simple energetics. So given that we already have access to download, filter, process data from Airflow, instead of now looking at the density of state, etc., why not we actually look at the following data? So consider that we have a binary A2B3 representatively. Uh, if it comes into contact with oxygen and forms sort of an oxide, it can form two separate elemental oxide. It can form a binary oxide or a combination of this. Some similarly with, let's say, sulfur. If we can actually if we can combinatorially generate all the possible reactions, then what we know is we can calculate a reaction energy, which is the energy of the reactants minus the energy of, sorry, the energy of the products minus the energy of the reactants, which is illustrated as this object. Uh, so delta E is energy of ABO3 plus AO2 plus 2 times BO minus 3 times E of O2 and minus the binary compound. The point is, all of these data is potentially available on Airflow. It's just that now we have to also, for a given pair of binary, search for all possible binary and elemental oxides. And once we know it's their DFT energy, we can calculate a reaction energy estimate of this. The same thing we can actually also do for, let's say, a reaction against H2O, which is water molecule, and H2S, which is sulfur dihydrogen sulfide. The reason to choose this is it can actually serve as a comparison of these two kind of reactions, because the difference among them is just, this is through hydrogen water and hydrogen sulfide, in which H2N gets separated. So somewhat energetics of these sort of reaction energies of these should be similar to these. So let's see what this actually tells us. Okay, this is the same thing but written in a more general format. So we generate all possible reactions using combinatorics, etc. We balance those reactions by calculating this NABO, NAO, NBO automatically. And once we have the downloaded data, we generate all possible reaction energy, and one can actually look at its distribution. Okay, so here is a typical distribution. The minima and the maxima of these reaction energy for each binary pair for oxygen, sulfur. And these are the trends of OS, oxygen and sulfur. Similarly, this is the trend for H2O and H2S. And as one can see that these trends are quite similar, which was expected, but these also tell us a way to actually shortlist a pair of binaries, which can potentially be a good candidate of against corrosion. And with this exercise, one comes from potentially no knowledge about the material space to shortlisting something like 10 binary compounds and similarly few ternary compounds to do this. So uh, these were the predictions, and I think this is for the record purposes, which can skip through. So we, from all the possible reactions, we can actually look at the least favorable reaction, which serves as a stability criteria against oxygen, sulfur, and so on. And this basically concludes the model descriptor-based calculations. Here, I will just show some sort of ab initio calculations, where, I mean, we already had done this calculation for 4D transition metals, and we extended this to post-transition metals. And we didn't have much of this data ourselves, so it was useful to actually calculate elemental and at a later stage binary estimate. I mean, for binary compounds, the estimate of sort of binding energy through ab initio calculation. One also reason is that several of these indium, tin, etc., their binaries are already among these lists, as you can see: silver, antimony, silver, tin, silver, indium, and so on. So as a first start, I started with few late transition metal and post transition metals. Systematically, we actually downloaded uh, all of their info from AFlow with corresponding ICSD and crystal structure, and the ones which had different crystal structure from on all of these lattices chosen, we generate a multi-layer slab and calculate the energy of the slab. Then we actually add Earth's orbits on potentially top, bridge, or hollow sites to calculate uh, their energy. And when we subtract this energy with atoms alone energy, which is basically this EB as energy of adsorbate plus slab minus energy of slab minus energy of adsorbate. So that gives us the estimate of binding energy. We did this calculation for these 11 lattice systems on each three surfaces using FHI AIMS, which gives us roughly 231 sets of calculation. Uh, so here is the illustration of top, hollow, and bridge site. So if we look at something which is, let's say, relatively tertiary, so atoms, I mean, if you put an adsorbate just on top of the site, that's the top site. If you put an adsorbate between two sites along the straight line at certain height, that's a bridge site. And if we have adsorbate which is away from all the straight lines in a hollow location, it's a hollow site. So we systematically generated all of these through a Python package called PyMatGen and push it to FHIAM's DFT calculation. And what we did come up with is the binding energy as a function of surfaces. So this is 11100 surface, in which on x-axis we have palladium to tellurium, and these color indicate basically bridge, hollow, and on top. So green is on top, hollow is orange, blue is bridge. And these are again oxygen and sulfur. And as we see that when we change the surface, the trend somewhat changes. These are basically the adsorbate movement. So when we actually put the atom on the surface and allow it to relax, it moves. So what we actually find is in most cases, this movement is somewhat similar. Huh? The stream seems to Stefano.
Yeah. Um, no, it froze, but now you're back.
Yeah, no, okay, I see. So Uwe just told me that my stream went offline. So I
Yeah.
don't know where did it go offline.
More or less here. I think if you start from here is okay.
All right. Okay. So I'll start here. Okay. So I was basically just saying that the actual overall atom movement is rather unpredictable. However, uh, this more or less horizontal curves suggests that uh, uh, no matter what the surface, the atom finds an optimal distance to the nearest atom and settles there in terms of distances. Now, here what we actually did was, so here we superpose our binding energy data with the actual enthalpy of formation. So the red uh, uh, closed squares and red open squares are the enthalpy of formation against sulfur, uh, oxygen and sulfur for these metals. And we see this trend. So it monotonically, this formation energy decreases uh, towards the silver, and it tries to increase and then reaches a maximum and goes down further. Now, our binding energies are not enthalpy of formation, but in a some scaled fashion, they serve the same purpose. So here we also see the same trend. So it from palladium it goes down more or less, and then increases and 111 surfaces. So this concludes the ab initio that we have to share, and I mean, just few a couple of months ago, before the coronavirus pandemic came up, we were actually discussing to potentially exploit the data that we have actually generated through our ab initio for a potential machine learning model that can be used that one can employ to map the surface potential to find uh, the optimal reactive sites sort of. Given that we have for NL number of lattice sites, we have 21 times those calculations, and each of these relaxation uh, generates a potentially large data for surface geometry, because when the relaxation occurs, so the ab initio softwares, they calculate the self-consistent DFT energy at that geometry. Then they propose a move. They move in that direction, which is in downhill in energy. Calculate energy at that uh, 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 geometry, and so on and so forth until they reach the minima. So if there is a number of intermediate steps whose data we have, so we have potentially a large number of data set to actually train a machine learning model. In each calculation through relaxation process, what we found that about 100 to 1000 steps actually were taken by the relaxation process, which potentially has a large, which gives us a large sort of geometry energy pair for us to train with. Something that actually I'm not going to actually cover today, given the time and the planning. When we actually do the similar calculations for binary alloys, this number of such calculation becomes much larger, and uh, that generates potentially an order of magnitude more data than elemental calculations. So there's a large data worth exploiting to for a machine learning model actually. And this, with this, I actually summarize that we have performed an ab initio calculation of the binding energy on three surfaces, and this is a tentative list of potential binaries actually that we actually came up. Uh, and in this process, we actually developed this data mining scheme, which can be used for other sorts of, basically a data mining tool for any other kind of machine learning problem actually. So I think for the moment, this is it. Thank you everybody for listening to me. This is my email address, and given that this is being sort of screened to YouTube, it is a customary thing to say, please subscribe to our channel. Press a bell icon. You must find a bell icon if you're not in full screen mode, uh, and subscribe to our YouTube channel of Computational Spintronics Group. and this is dedicated for doing machine learning for science, as the name suggests. Below is the YouTube channel, and I suggest Stefano to actually use a formal name such as ML4Science.
Thanks a lot. I guess we can give you a virtual clap of hands. Um, so I guess maybe we want to see whether there's some questions. Try to see whether the question works. So please write some question on the discussion dashboard. Let's see if there is anything.
Did we get anything?
Say again.
Did we actually get anybody's question? I think at the moment, majority of people listening are from our group only. We have to become popular or viral.
No, okay, but this was not even advertised, right? So that's okay.
Yeah, that's true.
Okay, so maybe okay, so that I guess maybe we can stop this one here. So
I think in this case, it's let me just say one thing actually. I mean, in this case, even if people have questions, please comment actually. So we're going to the YouTube style of language. So if you don't have any questions, please write your questions in the comment, which will, I mean, later hopefully appear. So this stream will appear as a video. One can pose questions hopefully there as well.
okay, and okay, so that's I guess maybe we can stop here. So thanks everybody for listening, and thanks Rajarshi again for being the guinea pig on this. All right, cheerio, bye bye.